Hi kiddos. So for this lesson, the question of the day, which let me explain that really quickly. For my physics kids, what I do is I always have them write down the title, which I now started calling the question of the day. And basically what that is which do you be able to actually answer by the end of the day. So all of your activities, all of the things that we do, everything will be geared towards answering that question. So for this one, what the question of the day is what happens when a reaction absorbs or releases energy? Okay, so the objective is you're going to go ahead and describe what happens in a reaction, okay, when basically there's this transfer of energy, and you're going to go ahead and do that, demonstrate that you understand this by doing an exit quiz. Okay, so last time we talked about how energy can be basically transferred in two different ways. One of them was through heat, the other one was through one of them was through heat and the other one was through work. So let me talk about work first. So work has to do with if you take your energy and you basically go ahead and you use your energy to go ahead and move something else. So for example, if I wanted to go ahead and pick up a book, that is me using or doing work. So I'm taking my energy from within my body and actually going ahead and transferring that energy to go ahead and move that book. Okay, now the second thing is heat energy, which is basically thermal energy, and that's whenever you are increasing or decreasing the heat of something or the temperature, which is a measure of heat. So that's, for example, like if you were to take a cup and put a cup of water and then you put some ice in there to cool it off, that's how you would have heat and energy being transferred as heat. So we also talked about potential and kinetic energy. So potential energy was stored energy. So like over here, okay, this woman has stored energy, and what is happening is basically she's like taking like an energy drink, or like, basically she's eaten, she has some energy inside of her, and so she's basically ready to go ahead and do some work. And then, so this again is an example of potential energy. Now, when she actually gets moving, then that becomes kinetic energy. So that's her using all of her stored energy and actually going ahead and using it. All right, so now that brings us to the first law of thermodynamics, and this is a really, really, really big law. It basically cuts across every single science subject that you will pretty much learn. Okay, and it's that energy is neither created nor destroyed. So basically what that means is that all that you can do with your energy is basically convert it into something else. You can't just use up your energy, and like even if you use up the energy, right, like at the end of the day you're tired, that energy just hasn't just like disappeared. You've used it out throughout the day and it's been transferred into other objects. So in other words, what that is saying is that the total energy of the universe is constant. Okay, so for example, like I said, like if you're really, really tired at the end of the day, that's because like during the day, right, you're eating, you have some energy, so you're moving around, like even like breathing costs you energy. And so what ends up happening is that energy is actually released out. So let's say you decide to go for a run, right? You're using your energy to actually go ahead and power you down that track. And as you're running, right, your body starts to get hot and it starts to release energy. So if you are the system, then that heat that you're producing because you're like running down the track, that's going into the surroundings. Okay, so the surroundings are basically absorbing that extra energy. Now, the same thing happens if the surroundings are releasing energy. It goes into the system. Okay, so we're going to come back to these two diagrams here. So for now, all that you need to know is that these are energy diagrams, and what these show is that these are the internal energy. So what I wanted to talk about is what the internal energy of a system is. And my neighborhood's like really busy right now for some reason. Yeah, people are out for like runs and walks, so if you hear all of that noise, sorry. There's a puppy. Anyway, sorry. So internal energy of a system is again the sum of all of the kinetic and potential energies of all the components in the system. And the way that we call that is we actually go ahead and we call that when people have decided to make all this noise. So once again, the internal energy of a system is the sum of all of the kinetic and potential energies of the components of that system. Alright, so here's an example of how molecules actually have this kinetic energy. So molecules are bending, okay? They're also like rotating. And then there's like symmetric stretching where like the molecules, the bonds between them, they're like stretching back and forth. And there's like translational where it's like basically kind of spinning around. So these are some examples of kinetic energy within a system, especially if you're looking at molecules, which is what in chemistry what we do. And the potential energy, the way that we have it is, again, remember that's potential energy is based on the location of the different objects. So over here, there's potential energy between this atom and this atom right here. Okay, and this is there's a water molecule, so these two are the hydrogens, and this one would be the oxygen. Okay, you don't need to know like all of these types of motion right now. You just need to know that that's how your system has energy. Now, because systems have energy, right? And in chemistry, we're always talking about reactions. So if a system is, let's say, hydrogen and oxygen, okay, so if you were to put them into like a little container and you want to study them, there's already some internal energy going on there. But if you put hydrogen and oxygen, what's going to happen is they're actually going to react with each other and they're going to start to form water. So that means that you're actually changing the internal energy. So what that actually means is that internal energy, or delta E, because you're changing that energy, is again the final energy of the system minus the initial energy of the system. So again, anytime that you talk about a change, oops, which I forgot to underline here, a change in something, it always means final. Let me use a different color. Use green. Always means final minus initial. Okay, so again, you learned this in physics, you learned this in chemistry, you're going to keep learning this in physics, you're going to keep learning this in AP Chem. So it's just one of those concepts that you need to remember. Okay, so again, change in internal energy is equal to the final energy minus the initial energy. Okay, so let's go ahead and look at what some of these diagrams mean. So again, this is the energy, internal energy of a system. So this is an energy diagram. And now what this is saying is that here's your initial state, right? So this would be like whatever state your molecules are in at the beginning. So taking, for example, hydrogen, oxygen, you could think of this as being like what the energy is when they're just reactants. And then the final state, wow, it's really noisy. Anyway, sorry. It's the final state is going to be like when it actually turns into water. So in this case, what happens is the initial state has a lot more energy than the final state. So because of that, okay, you have this change in energy, and it says that the final energy is less than the initial energy. Okay, now if you would actually subtract that out, because the final is much less than the initial, okay, so let me write that out. Actually, come back. So what that would mean is like, say for example you have delta E, right? This is your formula for change in energy, is equal to E final minus, that's like the worst writing ever, minus E initial. Okay, what that means is, what this is telling you is that this number is a lot bigger than this number. So let's say, for example, this one is going to be 10, and your final energy is like, I don't know, 2 or something. Well, apparently a Z. If you subtract this out, your answer is going to be -8. So, and this should all be in joules, by the way. So what this is telling you is that, again, because the final energy is less than the initial energy, then your change in delta E, which is your, oh my gosh, that's horrible. Yeah, I'm going to use a different color and try to draw better. So delta E, or your change in energy, is equal to negative 8 joules. So therefore delta E is negative, which means that it's losing energy. So that means that that energy has to go somewhere, and this is going to be an example of, and then we'll talk about it in a little bit, but like an exothermic. So think exo, think that you're getting rid of it, you're releasing it, okay? So now the opposite happens when your initial state, okay, is going to be less than your final state. So if it was reversed for the other, like for the other example I just gave you guys, right? If delta E is equal to E final minus E initial, then what this means is that according to this, right, your final state has a lot more energy, so this one is a lot bigger than this one. So let's say that in this case, your final energy is 12. I promise you that's a 12 minus 2. Then in this case, you're adding energy, and you're adding actually 10, so plus 10 joules. So delta E that's a delta, I promise. See if I can shade it in. So delta E, okay, in this case is going to be equal to a positive number, which means that the internal energy of your system is now going to be increasing. So anything that wherever you're putting things into something, okay, the prefix that we use for that is endo. Okay, now, so this brings us to changes in internal energy. So again, we're going to take that example of water, or the chemical reaction for water. Okay, and in this case, what you're doing is you're going from water and then you're breaking it down into hydrogen and oxygen. This is actually called hydrolysis, where you're breaking down water. So in this case, right, the energy is a lot higher for your final state. This is what you're starting with, and this is what you're ending with. So in this case, delta E is greater than 0, okay, which means that the final energy is greater than the initial energy. So because of that, that means that your system is actually absorbing energy from the surroundings. That means that you actually have to put a lot of energy in so that you can break this water, which is actually true. What you do is you basically pump electricity through it, and then that causes those bonds to go ahead and break, and that's how you form hydrogen and oxygen. And then this energy change, okay, so the name for whenever you have an energy change where you're gaining energy from your surroundings, that is an endergonic process. Where's my pen? Yeah, go back. Go back. So again, this is an endergonic process. Now, the opposite is that if you have hydrogen and oxygen, okay, and you were to put them together, okay, what's going to happen there is you're actually going to be releasing energy into your surroundings. So in this case, delta E is going to be less than 0, which means that you're basically losing energy, okay, and you're forming water because you're taking energy and you're basically breaking the bonds between these, putting them together, and then overall you're losing energy because you're forming this water. And that energy change is called exergonic. This guy right here. Okay, so again, important things to remember are these prefixes, so X being released, and then in this case, end or endo, oops, back, okay, so again, end or endo, that means you're putting things into that system. Okay. Now, back to when we were talking about heat and work. Okay, so if what's happening here is you're basically adding heat into the system, okay, which means that the surroundings is actually doing work on your system, and your change in energy is actually greater than 0. So basically, heat, work, and energy, they're all positive, which means that you're all increasing them. So energy is exchanged between the system and the surroundings again. So either exchanges either heat or work. So basically, delta E is equal to a combination of these two things, heat and work. And that's this formula here. So we learned about one, which is a change in energy. So that one's useful when they're already telling you what the energies are. But if you start talking about work and heat, then this is the formula that you're going to need to use right here, which is delta E tells you is equal to work plus, heat plus work. And the symbol for heat is Q, little q in this case. So once again, if you're exchanging heat between the system and the surroundings, if you're absorbing heat, okay, then that's an endothermic process. And remember, endo, think of it like into. But on the other hand, if you're releasing heat, heat is being released by the system into its surroundings, then that process is called exothermic. Okay. Now, that's pretty much the end of the lesson. And you guys had a quiz, an exit quiz, and for that one it says, it wants you to explain how the energy is being transferred for the following scenario. So if you have a candle burning on a table, how would you actually go ahead and transfer energy? And then would it go from the system to the surroundings, or would it go from the surroundings to the system? And once you decide that, then you have to decide if it's going to be an endothermic process or an exothermic process. Okay, so for you to get a 4 on this assignment, basically you had to write something like this. So when a candle is burning on a table, the candle is producing heat, which is thermal energy, and that is basically being released into the surroundings. So because you're releasing energy into your surroundings, that's going to be an example of an exothermic process. So if you notice I use complete sentences, I made sure that I use all of the vocabulary terms that we used today. So for example, endothermic, exothermic, I talked about systems and surroundings. Wait, did I put in systems? No, but it should be in there. Okay, so that's it for your exit quiz. And then I think these were the problems that I gave you guys, 5.8, 5.15, and 5.27. If these weren't it, just verify for me, please. And that's pretty much it for this lesson. I'm going to go ahead and upload it right now to Google Drive. If you have any questions, let me know. Other than that, thank you guys. Have a good weekend. Bye.